to integral V1 to V2 of P dV. And remember, integral is a measure of the area under the graph. So we will now look at that as we go on. Let's now talk about what is called an isobaric process. Now, do you remember when you talked about Boyle's law? We said Boyle's law describes an isothermal process. You recall that? What is an isothermal process? An isothermal process is a process where the temperature remains a constant. What is an isobaric process? An isobaric process is a process where the pressure remains a constant. In an isobaric process, the pressure remains a constant. So in that case, we can represent it like this. The pressure does not change. When volume changes from V1 to V2, the pressure does not change. And this makes it easy for us to calculate the work done. And the work done in this process, because the pressure does not change, the area is now a rectangle. You don't really need an integration in this case. The work done here, W equal to integral V1 to V2 of P dV. Remember, integral of P dV is a measure of the area under the graph of pressure against volume. You understand that, isn't it? So this is a graph of pressure against volume, and pressure remains a constant. That means this is the area that represents the work done. So since pressure is a constant, we can take that out of the integral. That becomes pressure times integral V1 to V2 of dV. What is integral of dV? Integral of dV is V. So that will be P times V. Lower limit is V1, the upper limit is V2. And you know how to do these kind of things. It will be P times V2 minus V1. Replace V by the upper limit minus replace V by the lower limit. You can see work done is P times V2 minus V1. If you look at the diagram here, P is a constant, that is your P. P times V2 minus V1 is the area of this rectangle. This is P and this is V2 minus V1. Therefore, this is a measure of the area under the PV diagram. So, work done by a system can be obtained as the area under the PV diagram. It's a very important relation. I want you to remember these relationships. All right. The total work done when volume changes from V1 to V2 at constant pressure is W equal to P times V2 minus V1. Now, in an isobaric process, pressure remains a constant, and this is the process that we have just talked about. So W isobaric, work done for an isobaric process is P times V2 minus V1. Reinforce that idea one more time. Now, okay. Now, pressure volume, that is PV diagrams, are primary visualization tool for the study of heat engines. Now, as I told you, you come to school and back or go many places, carry with you a heat engine. Your car has a heat engine, internal combustion engine, and the study of such engines can be made easy by looking at the PV diagram of the engine. Now, here I have a PV diagram. Now you notice the stages 1, 2, 3, 4, 1. Now, this actually summarizes the complete working of the engine of your car. Now, do you know really how the engine of a car works? Now, let me take a minute and try and see if I can explain that to you. Now, your car engine has, I'm just going to take one cylinder. There's a cylinder, there is a piston, and the piston is, of course, connected to the crankshaft. Now, to make your engine start, in order to start the engine, you need to supply some extra external energy, and that is what the battery is for. So, when your battery first starts your car, the piston is pulled back. When the piston is pulled back, a valve will open and fuel will spray. Fuel, of course, mixture of fuel and air will spray into the cylinder. And then, when the mixture has been sprayed, then the piston goes forward. So the first stage is called the charging stroke. The engine is charged. What is the second stage? In the second stage, the piston is pushed forward, compressing the gas. You see, this is where the compression takes place. That means the gas inside is compressed to a very small volume. What will happen? The pressure and the temperature increases. So this is called the compression stroke. The second stage is the compression. And now what happens? At this particular time, your engine will produce a spark. Now, when a spark is produced into this compressed fuel and air, which is at a very high temperature and pressure, it explodes. And that explosion, that is the first time your engine comes to life. It is that explosion that produces that energy. So, you have the third stage. The third stage of the working of the car will be that big explosion in there, which will throw the piston backward. The piston is thrown back with that explosion. And finally, when the piston is pushed forward, all the spent materials are taken out. That is the exhaust. So these are the four stages. The third stage is called the working stage, and the fourth one is called the exhaust. So what happens? Heat is added. First of all, you have work done on the gas. This is, can you recognize this stage? The piston pushes the gas forward. Work is done on the gas. You can see that is given by the area below. This is a PV diagram. So if this stage is work done on the gas, that is this stage when the piston is pushed forward, given by this area. Then heat is added. How is heat added? The spark plug explodes. Once the spark plug produces a spark, there is a great explosion. Heat is added at constant volume. And then what happens? That great energy, the work is done by the gas. What happens? The piston is pulled back. The volume increases. The pressure decreases. This is the time when your engine does useful work. Isn't it? Yes, the engine does useful work given by the area under the graph there. Now that means, let me go back and show this one more time. Now, if this is the work done on the gas, I'm using the blue lines to represent that. then this will be the work done by the gas. You see that? The work done on the gas is the blue area. Work done by the gas is the red area. Therefore, what is the useful work done? It's the difference between the two, and that is the area shaded. So during this 4 cycle, the useful work done by your car engine is this. Okay, let's move on. So since the engines usually involve a gas as a working substance, the ideal gas law relates to the PV diagram to the temperature, so that 3 essential state variables for the gas can be tracked through the 4 cycles of the engine. I gave you the 4 cycles. You see that? You got the charging stroke, the compression stroke, the heat added, then the working stroke, and then the exhaust stroke. Since work is done only when the volume of the gas changes, look at this, work is done at 2 stages. Work done on the gas, the volume changes. Work done by the gas, the volume changes. These are the only stages when the work is done. Remember, work is PDV. When there is no volume change at this stage and at this stage, there is no work done. Alright, let's see if I can give you an illustration. If your car is a 4-cylinder engine like mine, it will sort of work like this. Now look at the 4 cylinders. Let's concentrate on 1 cylinder and look at the 4 different strokes. What are the 4 strokes I gave you? First is the intake stroke, taking in the fuel, then the compression stroke, then the working stroke where the energy is produced, and then the exhaust stroke. Alright, here is the intake. Now here is the compression. This is the combustion working, and then the exhaust. You see? And if you notice, each of these cylinders will go through these 4 cycles one after the other, so that energy gets delivered. Remember, the useful energy gets delivered only on the combustion stroke, only when the yellow stroke. You see, useful energy here, useful energy here, useful energy here, and useful energy here. It is one after the other. That means useful energy is delivered to your crankshaft continuously because of the 4 engines working one stroke after the other. So one more time, the yellow is the useful stroke. There is useful, followed by the useful energy, followed by combustion, followed by combustion. So each of these engines deliver energy to your engine at a continuous rate so that your car will run very smoothly. Now, if there is only one engine, how will your car run? It will go chuk, chuk. Is that right? Okay, I don't think you want that. For each cylinder, the area enclosed by the cycle on the PV diagram is proportional to the work produced by the cycle. So energy is delivered to the engine one after the other by each of the cylinders. If you have an 8-cylinder car, you can see it gets much more energy. So a sports car should definitely have more than 4 cylinders. Well, I'm going to stop this part of the lesson here. I'm going to record a second part of what is this called? 2.3, I suppose, a little later. So I will see you for that a little later.